Hi, I'm Evan Hartnett. This is my Physics 2012 Lab 5, Magnetic Braking with Faraday. The overall purpose of this lab was to gain a better understanding of Faraday's law by dropping a magnet through a conductive tube of aluminum foil, and then modeling the magnet and tube interaction computationally, and then comparing the computation with the observed data. I found the average recorded fall time of my magnet in real life was 1.576 seconds, whereas the model predicted a fall time of 2.237 seconds. The physics principles for this experiment include Faraday's law, the magnetic field of a bar magnet, Biot-Savart law, Newton's second law, magnetic flux, and Lenz's law. The assumptions I made were that there are no external magnetic fields acting on the bar magnet and no other forces acting on the magnet except for the magnetic force created by the induced current and gravity. For this experiment, the system was the bar magnet and the roll of aluminum foil through which it traveled. The surroundings were everything else. The initial conditions were holding the magnet above the aluminum foil roll with the bottom of the aluminum foil roll above the ground. I then determined which end of the bar magnet was the north pole of the magnet using a magnetometer app. Then I measured the roll of the aluminum foil to determine dimensions of the tube, its length, radius, and foil width. I then held up the roll foil vertically without resting the bottom on a surface to allow the magnet to fall through, then dropped the magnet 5 times and recorded entry and exit times via phone video. From this data, I collected an average fall time. While performing the experiment, I noticed that the magnet fell to the ground more slowly in the tube than outside of the tube. I also noted that a ferrous tube wouldn't work for this experiment because the magnet would simply stick to it. Shown on the bottom left of this slide is my data for the time taken by the magnet to fall through the tube. And shown on the right is my data for the size of the tube as well as the mass and magnetic dipole moment of the bar magnet. To develop my model, I first used the data shown on the previous slide to set up a model for the roll of foil as well as my bar magnet. I then used my Lab 3 code to create a function to calculate the magnetic field of the bar magnet. I then developed code to calculate the rate of change of the flux through each ring due to the falling magnet. I then divided the rate of change of flux by the resistance of the ring to calculate the current in the ring. Then I computed the typical B field at each ring using this current. Then I calculated the gravitational force acting on the magnet, and I took that and added that to the magnetic force acting on the magnet to get the net force acting on my bar magnet. Once I had this quantity, I was able to update the position and velocity of the bar magnet continuously. Shown here are screenshots of my computational model output. On the left is the rod represented by the gray cylinder with the bar magnet falling from the top to the bottom. Then on the right is my velocity versus time plot for the velocity of the bar magnet as it traveled through the tube, as well as the calculated time in the tube of 2.237 seconds. To correctly interpret the simulation, it's important to know that the change in magnetic flux increases in the negative y direction, which is the direction the magnet falls. If viewed from the top of the tube, the red ring shown on the last slide corresponds to clockwise direction of current, and the blue ring corresponds to counterclockwise direction of current by Lenz's law. If the magnet were to be flipped, then the magnet would still be slowed as it fell, but the ring current directions would be flipped as well. My recorded average fall time in real life was 1.576 seconds, while the model computed 2.237 seconds. The computational system would be made more accurate by considering air resistance and the Earth's external magnetic field. The velocity versus time plot shows that the magnetic and gravitational forces acting on the magnet are initially not balanced, but eventually level out. Some sources of error in this experiment include inaccurate timing when measuring the falling time of the magnet in real life. I may not have been able to scrub to exactly the right timestamp in the video where the magnet entered and exited the tube. There also may have been errors calculating the dipole moment of the bar magnet from Lab 3, which may have been perpetuated into this lab. The computational model also does not account for air resistance or the Earth's magnetic field, and the roll of foil had a roll of cardboard within it, potentially weakening the induced current. If the resistivity of the conductor was reduced as close as possible to zero, the current would increase. This in turn would strengthen the force of the magnetic field and slow the fall of the magnet even further, resulting in a longer fall time, and eventually preventing the magnet from entering the tube altogether. If holes or slots were cut into the tube, there would be less rings of current, resulting in a weakened force of the magnetic field. This means the magnet would fall faster, resulting in a shorter fall time. The model would have to account for this by using less rings.